Hey guys, as many of you know, Giovanni and Steven recently published a paper titled A Mechanistic Derivation of the Bitcoin Price Power Law, Network Adoption Dynamics, and Generalized Metcalfe Scaling. Even though we have all of this info on the power law theory that we have shared through social media over the years, it is great that we now have a scientific paper as well. And it has already been downloaded over 8,000 times as of the making of this video, which is really rare for a scientific paper. And clearly this will serve as a very important reference point for future Bitcoin-related science. So let's get to it. First, the authors explain the methodology and how they derived their data. And as you can see, daily USD closing prices were assembled from two main sources: Glassnode on-chain data and historical exchange data. And for dates prior to the first reliable exchange price data, the price signal is relatively sparse and unreliable. And these observations were thus excluded, yielding a clean series starting at t equals 560 days. The authors also explain how they derived how many Bitcoin users there actually are. They say that the metric of non-zero addresses is a widely used proxy for the count of economically active network participants. And they also acknowledge that single users may control multiple addresses, and that dust addresses may persist after effective abandonment. So why is this paper so important? As you all know, most people who talk about the Bitcoin power law just care about the price power law. But what the paper really proves is that the power law isn't just another random model that tries to fit a curve to the price. Instead, it argues that the exponent itself can be derived from two underlying mechanisms. The central result is that Bitcoin's price follows a time-based power law. Price is proportional to time raised to the power beta, whereas beta is about 5.7. And this exponent emerges from the interaction of adoption dynamics and network valuation. Even though we know that Bitcoin follows a whole host of power laws, which we have covered in our Physics of Bitcoin videos, this paper really focuses on the duality between two particular power laws. On one side, you have adoption. The number of economically active participants grows over time as n of t, being proportional to t raised to the power beta a, where beta a is approximately 3. On the other side, you have valuation. The price of the network scales with its size according to a generalized Metcalfe law, meaning price is proportional to n raised to the power beta m, where beta m is about 1.84. As you know, individually, both of these relationships have been observed by Giovanni before. What this paper does is connect them in a scientifically falsifiable way. When you combine them, you get the key results. Price as a function of time is proportional to n of t raised to beta m, which is proportional to t raised to beta a, all raised to beta m. So in total, proportional to t raised to beta a times beta m. Numerically, this gives beta of about 3 times 1.84, or roughly 5.6, which closely matches the directly measured exponent from price data. This is the core contribution. The Bitcoin price power law is not treated as a standalone empirical regularity, but as a composition of two deeper scaling laws. And adoption determines how fast the network grows in time, and Metcalfe-type scaling determines how that growth translates into value. And the price trajectory is simply the product of these two effects. And the implication is also very important. It suggests that Bitcoin's long-term price behavior is not primarily driven by narrative cycles or external shocks, but by structural properties of the network itself. And if adoption follows a predictable diffusion process, and if network value scales in a stable way with participation, then price inherits that structure automatically. And in this view, the familiar boom-bust cycles are not the main story. They're deviations around a deeper deterministic trend. The empirical results support this interpretation. The power law fit remains stable over more than 15 years of data, with a high R squared and residuals that are pretty stationary rather than drifting. And deviations from the trends appear as cyclical oscillations, roughly aligned with the halving cycles. But these fluctuations remain bounded and do not accumulate over time. Obviously, there has been a lot of recent debate on the topic of Fourier cycles and whether they still hold true. And Giovanni and Stephen have also been working on a log periodic interpretation of the cycles. In fact, many years ago, when we first discussed the power law with Giovanni, before we became known on social media, he was leaning more in the direction of this type of model. And we will have to see which interpretation is more true over time. Anyway, this is not what this paper focuses on. The important thing about the power law trend is that the exponent itself appears stable, whether estimated globally, in rolling windows, or through alternative methods like scaling collapse. It consistently falls in the same very narrow range, and this reinforces the idea that beta behaves like a structural parameter, not a fitted artifact. So this is my favorite part of the paper. We have all three power laws displayed visually in a very beautiful way in a log-log plot. First, we have the adoption power law with a beta A of 3, then also the Metcalfe scaling law with a beta M of 1.8. And finally, we have the combination price power law with a beta of 5.6898. As you can see, when you combine these two power laws, they beautifully form this price power law. So what is the key takeaway here? Well, the duality also explains how to think about the model's limits. The power law holds only as long as both underlying relationships hold. If adoption stops following a cubic-like growth because of saturation, changes in user behavior, or measurement breakdown, then the time scaling no longer applies. Likewise, if price becomes decoupled from network size due to financialization, leverage, or custodial concentration, then the Metcalfe relationship also breaks down. And in either case, the composite power law would fail. So a 3 sigma drop below the power law to crazy levels like 10K for a year or so would imply that even though the theory has been useful for observing growth so far, something has now fundamentally changed and the power law has tapered off. More generally, the model depends on Bitcoin remaining a network-driven system. If external factors begin to dominate price formation, or if the system develops a characteristic timescale, for example through maturity or saturation, then the assumption of scale invariance would no longer hold. A clear sign of breakdown would be residuals that drift over time, increasing variance, or a persistent change in the estimated exponent. In that sense, the paper is less about predicting price and more about reframing what Bitcoin is. It treats Bitcoin as a system whose behavior emerges from the interaction of network growth and network value. And the dual power law, adoption in time and value in size, is the mechanism, and the price trajectory is actually the outcome. Toward the end of the paper, the authors also describe how they arrived at these conclusions. As some of you guys know, Giovanni already started describing the power law relationship in 2014, and that relationship was the one between price and address count. And he also connected it to Zipf's law and Metcalfe scaling. And then obviously over time, he started finding more and more power laws and connecting it all together. And also he's describing that other authors have arrived at relatively similar conclusions. For example, Wheatley developed a generalized Metcalfe's law for Bitcoin with an exponent of 1.69. And the author's own measurement of 1.84 is very close to that, so the data matches. So the paper concludes that Bitcoin's price over time has followed a very robust power law with an exponent of 5.69 over the past 15 years or so. And this exponent is not random, it's not a free parameter. It factorizes both of the other power laws. So beta A times beta M would give you the answer of 5.6, which is within 1.6% of the observed 5.69. And finally, the authors also performed 3 separate tests of scale invariance to confirm the power law beyond regression. As mentioned before, these results suggest that Bitcoin's long-term price growth is not primarily a speculative phenomenon, but a deterministic consequence of its network architecture. The power law itself is the attractor. Anyway, that's all for this video, and I definitely recommend giving this paper a read. Stay tuned for more. This is Saverio speaking, and as always, thanks for watching.